We are going to explore an invisible, energetic phenomenon that constantly surrounds our planet. This phenomenon is known as Schumann resonances, which are global electromagnetic waves that act as a natural background hum continuously circling the Earth.
A global background hum sounds wild. So what exactly is creating these waves?
Believe it or not, they are constantly powered by the thousands of lightning strikes that occur around the world every single minute. Every flash pumps electromagnetic energy into this global system.
I had no idea that much lightning was happening at any given moment. But why do the waves circle the globe instead of just escaping out into space?
They actually get trapped in a specific space in our sky. The physical ground below and the upper atmosphere above act like boundaries, keeping that electromagnetic energy contained as it travels around the planet.
So the Earth is basically a giant natural echo chamber for lightning storms?
Exactly. And because this hum is completely invisible, proving it existed was a fascinating challenge. To understand how it was finally discovered and verified, we can trace its history directly through the core steps of the scientific method.
That sounds like a perfect way to see how an invisible theory actually becomes a proven fact.
To understand the science of Schumann resonances, we first have to look at a fundamental physical property of our planet. By the early 1950s, scientists had established a crucial observation, which is that the Earth's surface is actually a giant electrical conductor.
Wait, when you say the Earth is a conductor, do you mean everyday dirt and rocks can carry an electric current?
Exactly, along with our oceans. People actually figured this out back in the 1800s, thanks to early telegraph engineers.
How did building telegraph lines prove the ground was conductive?
Normally, a complete electrical circuit needs two wires, with one to send the current out and one to bring it back. But engineers noticed they only needed to string up a single copper wire in the air.
So what did they use for the return path?
They just buried copper plates in the dirt at both ends of the telegraph line. The electrical current traveled out through the overhead wire and then used the miles of open ground between the plates to travel back and complete the circuit.
It is wild that the current could just travel through miles of Earth without getting lost or just fading out.
It really is. And because the circuit completed with very low electrical resistance, it proved the Earth's surface is a highly effective conductor. Gathering this kind of concrete observation is always the first step in the scientific method.
And that established the groundwork for discovering those Schumann resonances you mentioned?
Precisely. This basic physical fact became the crucial starting point for the theories that followed in the 1950s. We are turning our attention to the sky to explore a fascinating, invisible layer of our atmosphere that actually conducts electricity. Back in 1901, Guglielmo Marconi managed to transmit a radio signal all the way across the Atlantic Ocean.
That sounds like a massive milestone. But how does sending a radio signal across the ocean relate to the atmosphere conducting electricity?
It comes down to the simple fact that radio waves travel in straight lines. Because the Earth is curved, a straight shooting signal sent across the ocean should have simply sailed right off into space.
Oh, I get it. Since the ground was curving away from the signal, something in the sky had to be bouncing it back down to the receiving station.
Exactly. And scientists guessed that an invisible electrically conductive layer high up was acting like a giant radio mirror. To prove it, in 1924, a physicist named Edward Appleton aimed radio waves straight up into the air.
Did he just wait to see if a radio echo came back down?
Yes. He measured the exact time it took for those reflected waves to return to his receiver. By timing that round trip, he proved the mirror was real and confirmed the existence of the ionosphere.
So that upward ping mapped out exactly where this conductive roof was located.
It did. Appleton's returning waves showed that this ionosphere is a layer of ionized gas sitting roughly 60 to 100 kilometers above the ground. Let's explore how raw forces of nature, like a lightning strike, emit invisible signals that sparked some of our earliest physics theories. Every time lightning flashes, it's actually a massive sudden movement of electrical charge that creates an outward ripple in the surrounding electromagnetic field.
Are those ripples what causes that popping static sound on old radios during a thunderstorm?
Exactly, because that suddenly accelerating charge turns the lightning bolt into a powerful broadband transmitter. It blasts out a chaotic pulse of energy across a huge spectrum, including what we call extremely low frequencies, or ELF.
Did scientists realize right away that lightning was broadcasting these low-frequency waves?
The mathematical hint started way back in 1893 with a physicist named George Fitzgerald. He suggested that because the ground and the upper atmosphere are both electrically conductive, the air between them could act as a giant resonance chamber.
So the earth and the sky would bounce those lightning waves around, almost like the hollow body of a guitar amplifying sound?
That is a fantastic analogy, but at the time, Fitzgerald's idea couldn't be proven in the real world.
Was that simply because the technology to measure such extremely low frequencies didn't exist yet?
That was a huge part of it, yes. On top of lacking the right tools, nobody had directly proven the existence of the ionosphere yet, so his atmospheric guitar body remained a purely mathematical concept. Moving into the second phase of the scientific process, we reach the point where an idea transforms into a concrete prediction. The second step is formulating a hypothesis, and a fascinating example comes from physicist Winfried Otto Schumann in 1952.
What exactly did he propose?
He suggested that the space between the conductive Earth and the conductive ionosphere above it forms a giant spherical resonant cavity. He hypothesized that global lightning constantly rings this space like a massive bell, creating stable, natural standing waves.
That sounds almost poetic, but how does the Earth ringing like a bell actually make for a strict scientific hypothesis?
It comes down to one essential rule, which is that a scientific hypothesis must be falsifiable. This means it has to make precise predictions that an experiment could potentially prove wrong.
So if a theory cannot be tested and explicitly disproven, it falls completely outside the realm of science?
Exactly right. Schumann made his hypothesis highly falsifiable by calculating exact mathematical numbers based on physical laws, the Earth's physical dimensions, and the speed of light.
What specific numbers did his math predict?
He calculated that if this cavity resonance existed, there had to be a fundamental frequency peak near 10 Hz, which was later refined to 7.8 Hz. He also predicted higher harmonic peaks at roughly 14, 20, and 26 Hz.
I see. So if someone ran an experiment and found no peaks at those exact frequencies, his hypothesis would be proven false.
You have it perfectly. Offering of strict, testable conditions that can be disproven is the true mark of a strong scientific hypothesis. To really prove a scientific theory, we have to figure out how to properly test it in the real world. This brings us to the third step of the scientific method, where researchers design an experiment to gather empirical data under strictly controlled conditions.
So how did Schumann approach this step in 1954?
He and his doctoral student Herbert Koenig had to start by building custom equipment. They needed devices sensitive enough to detect extremely low frequencies, which are often abbreviated as ELF.
I imagine measuring extremely low frequencies is tough with all the electricity we use every day.
Exactly. Human-made electromagnetic interference was their biggest hurdle. Everyday infrastructure like power grids and electric railways can easily drown out subtle natural signals.
How did they manage to block out all that industrial noise?
They used distance to their advantage by setting up two separate monitoring stations. They placed one right in Munich and a second quiet reference station far out in the countryside.
Oh, I see. By comparing the data from the city and the country, they could filter out the local interference.
Spot on. By looking at the data from both locations, they could successfully isolate the true natural background signals of the Earth from all that local industrial noise. We're at the point in the scientific process where we actually have to record and analyze the experimental results. For Schumann and Koenig, this meant trying to capture natural extremely low frequency, or ELF, signals from the environment.
What kind of equipment did they even use for that?
They had to rely on the technology of their time, using analog amplifiers and traditional paper and ink recorders. With this setup, they actually observed weak wave-like oscillations right in the 8 to 9 Hz range.
That sounds like a success. Was that 8 to 9 Hz range close to what Schumann had mathematically predicted?
It was very close to his prediction. But there was a major catch. The limits of their analog technology made it incredibly difficult to cleanly separate that faint signal from local interference.
Why does analog equipment struggle so much with background interference?
Analog systems continuously record all the electrical noise in the environment as one blended signal on the paper. Without modern digital filtering, isolating just that specific 8 Hz wave is like trying to isolate a single whisper in a crowded, noisy room.
So they had a signal, but they couldn't be entirely sure it wasn't just local noise.
Exactly. Because of that uncertainty, this initial measurement provided a very promising preliminary result, but it wasn't enough to serve as definitive proof just yet.
It is always a big moment in science when a brand new hypothesis is put to the test by outside researchers. This brings us to the 5th step of the scientific process, which is replication and peer review.
So who actually stepped up to see if Schumann's predictions about these electromagnetic frequencies would hold up?
Between 1960 and 1963, Martin Balzer and Charles Wagner at MIT's Lincoln Laboratory decided to repeat the experiment, but this time they had a huge advantage because they could process their data using early digital computers.
How did having those computers change the way they analyzed the background noise?
It allowed them to run a mathematical technique called a Fourier transform. Basically, it takes a messy signal that is changing over time and translates it into a clear spectrum, showing exactly how much energy exists at each specific frequency.
Oh, so instead of just looking at a wave of random static, they could see exactly which frequencies had the most power?
Exactly. And their results clearly showed 5 distinct energy peaks rising above the background noise. Those peaks sat at approximately 7.8, 14, 20, 26, and 33 Hertz.
Which is exactly what Schumann's mathematical models predicted in the first place.
Spot on. Because the independent data matched the predictions so well, the hypothesis successfully survived the test of falsifiability and was officially accepted as a confirmed physical phenomenon. When it comes to actually finding and analyzing the Earth's natural electromagnetic background, scientists have to use some incredibly sensitive tools. These Schumann resonance signals are so extremely weak that picking them up requires specialized antennas.
What kind of antennas do you need to catch something that faint?
The most common method measures the magnetic field using huge induction coils, which are loops of wire wound thousands of times around a metal core. They usually point one north-south and one east-west, and they can detect magnetic fluctuations as tiny as 1 picotesla.
1 picotesla sounds unbelievably small, but you mentioned multiple types of antennas?
Right. They also measure the electric part of the wave using a vertical ball antenna or a metal plate. That captures the vertical electric field, which is typically only around 300 microvolts per meter.
With signals that tiny, wouldn't everyday electricity and power lines completely drown them out?
That is a huge challenge, which is why the raw signals are amplified thousands of times and run through electronic filters. Those filters strip away intense human-made interference, especially the 50 or 60 hertz hum from our power grids.
So once you have this perfectly filtered, continuous digital recording, how do you actually spot the resonances?
Computers apply a mathematical tool called a fast Fourier transform to the data. This converts the long timeline of voltage changes into a visual graph called a power spectrum, where the resonances finally appear as rounded peaks above the background noise.
Are those peaks always at the exact same frequency, or do they move around?
They actually shift slightly throughout the day. Researchers fit a mathematical curve to each peak to precisely track those changes, which happen as the ionosphere shifts in response to sunlight and global weather patterns.